ladies and gentlemen, and boys and girls. This is what New Zealand says, right? It's my great pleasure to welcome you tonight for this third lecture of the series in quantum computing. As you know, the aim of the Gibbons series is to bring advanced topic in computer science to the general public. And so far, we had with the first lecture, there was a kind of a general intro done by our excellent Dr. Michael Dunedin. Then we moved on to the impact that quantum computing might have to cybersecurity and in particular cryptography, done by the brilliant Professor Stephen Galbraith. And tonight is my honor to introduce you to Professor Michael Bremner. Michael is a professor of software engineering at the University of Technology, Sydney, and works at the Center for Quantum Software and Information. And he's also the leader of the node, I have to read, Australia Research Council Center of Excellence for Quantum Computation and Communication Technology. Got it all right? Yeah. Yep. So Michael's research basically is focusing on finding interesting tasks that can be executed by or experimental executed by current architecture in order to then scale up for more advanced architecture in the long term in quantum computing, of course. So without any further ado, Michael, the floor is yours, and I'm looking forward to your talk.
Well, thanks very much for such a lovely introduction and way to get CQC2T said correctly, because it's like impossible to say that the first time in public. It's really lovely to be here. I've never been in New Zealand before. This is the first time I've been here. Walking around Auckland the last day or so, it's kind of amazing. I'm really interested in coming back because it seems like a really nice city, and everyone's got a rugby, which is so weird because we're terrible at it at the moment. So I'm here to talk about, well, this is a public lecture, which is always a bit challenging in a topic which is essentially going to be, really quietly, computational complexity theory. So I'm going to try and make this very general audience, but I'll probably fail and end up targeting a few specialists in the audience who will probably be the only ones who understand what I'm actually trying to say. And even then, I probably won't get the pitch right because I aim too low in the first place. But let's see how we go. So the work I'm talking about has been basically a long-term research project which I started to work on probably back around 2007 with some of my close friends, Ashley Montanaro, Daniel Shepard, and Richard Joseph, way back when I was a postdoc at the University of Bristol. This work has grown a lot over the last 10 years, and a few years ago, I began working on this with the team at Google, mostly Sergio Boisho, the Smolansky brothers, Brian Babouche, and the others there up on that list. So basically, we should start at the beginning if I'm going to explain this properly. So for those of you who are looking for a good introduction to quantum computing, or a really interesting introduction to quantum computing, you should have a look at Quantum Computing Since Democritus by Scott Aronson. It's a neat little textbook which came out of a philosophy of computing course that he taught at MIT a few years ago. I think if you read, I think it says on his foreword, he was trying to write a philosophy book and a computer science book and failed at doing both at the same time. But it's a really interesting book, and I really highly recommend you read it. It's really nice. So he says in the book that quantum computing presents a serious challenge to the so-called extended Church-Turing Thesis, and that is that any function naturally to be regarded as efficiently computable is efficiently computable on a Turing machine. So I don't know how familiar everyone is with the Turing machine model of computing, but essentially it's this very old notion of computing where you print symbols on a tape, and it goes backwards and forwards, and there's a head which writes symbols to a tape, and an algorithm is described by the symbols on the tape, and the head updates according to what it sees in the algorithm. So it's a very archaic notion of computing, but nonetheless it captures what we regard as everything we regard as being computable, but very importantly, the amazing laptop I have in front of me, the supercomputer over at NASA, and all the computing devices we use, essentially up to polynomial factors, work in the same way. They're big polynomial factors, to be sure. It's a lot faster. There's a lot more memory. You can read and write really quickly over many, many things simultaneously, but essentially the model of computing is the same. quantum computing is an example of a model of computing which is subtly different from the Turing machine model. And it's one of a few which vary from the Turing machine model, but what's interesting about quantum computing in particular, it seems to be vary in a way that we might actually be able to build it. And as such, this is what makes it a significant challenge to the extended Church-Turing thesis. Now, why is it a challenge, and what's going on here? Okay, so here's some data I pulled from reading annual reports for the supercomputer hours at the Oak Ridge supercomputing facility in the US back in 2014. So you can see here that, this is basically for all the publicly funded projects that have been run at Oak Ridge. These are the hours that they allocated. The stuff in the green here is basically all doing the problem of quantum simulation, which is a hugely important task. This is my way of explaining it's a hugely important task. A few of these other things here are also arguably quantum simulation, could be improved by quantum simulation. So quantum computers are basically a device that is specifically built to do certain quantum simulation tasks efficiently. And I'll explain a bit more how that happens later in the talk. But this is a task which actually turns out to be very, very hard to do on a classical computer. I mean, I can argue it by just brute force and saying, look how much time they're spending on supercomputers doing this. This is obviously really hard. But you can actually make this argument much more formal. And this is basically what I'm going to talk about during this talk. So in the late 70s and early 80s, a whole range of computer scientists began talking to a whole range of physicists about the nature of computing. And this culminated in a talk given by Richard Feynman in 1982, where he proposed this notion, which we now call quantum computing. And basically the notion was, he said, okay, imagine, through the 60s and 70s, we were getting pretty good at controlling quantum systems. Or we were beginning to learn how to control fundamental quantum systems. So, quantum optics was taking off, actually, in part due to a lot of good theoretical work was coming out of New Zealand, like Dan Wall's team and others. And generally around the world, people were beginning to, we sort of grappled with the foundations of quantum mechanics in the 30s. Then sort of nuclear physics happened, and then high energy physics happened, and then gradually people were like, hang on, what about cold physics? And
sorry, it's just at the back, it's just slightly difficult to hear you. Would you be able to just keep the volume just slightly?
Is that better? I'll speak a bit louder. Okay, thanks. All right, so in the 60s and 70s, we were getting a bit better at quantum control. Physicists were beginning to develop methods for doing this. I mean, it was still pretty rudimentary, and it's very rudimentary compared to what we do now, but it was beginning to happen. And Feynman proposed, well, he said, okay, so say we get particularly good at quantum control, maybe we can identify certain classes of physical systems where we can manipulate them in such a way such that they can mimic sort of all the naturally occurring physical systems that we see. Maybe, essentially that's a computing device. So, maybe that could turn into a model of computing. And gradually over the next few years, it was formalized as a model of computing, most notably by David Deutsch, and then a series of other people through the 80s and early 90s began to build around this idea. But to be clear, this was really, at the time, an intellectual exercise. The number of people doing it was very small, it was very crossed over with philosophy, it was just a thing theorists were doing because it was a super interesting question. And that was true until Peter Shor came along, essentially. And you would have heard last week, Stephen's talk, that what Peter Shor did was to show that the factoring problem can be solved efficiently on a quantum computer. So to really clear how big a deal this is, a device which had been primarily designed for this task of simulating quantum systems was now seen to be able to solve a completely different problem in a completely different area of computer science and do that efficiently. What's more, it was a problem which many people still argue, couldn't believe there was any sort of physical computing device that could be built that could possibly solve this problem efficiently. So Peter Shor showed this, he proved it. It's like an absolute tour de force in quantum algorithms. Actually, it's one of these funny things, as someone who works in the space of quantum algorithms and complexity theory, people saying, but what have you guys done since Shor's algorithm? And you're like, it's like saying, what have we done since general relativity? It's like we started at the top and we're moving downhill from here. It was a really big breakthrough, and it was an amazing piece of work, built on some other amazing pieces of work by Dan Simon, Richard Joseph, and David Deutsch. Okay, so that was back in the 90s, and so you can understandably, it's a big crypto thing, so three-letter agencies around the world kind of got involved. But also, it it was enough interest for the experimental physicists and theoretical physicists who weren't really doing quantum computing to begin to say, hang on, can we build these things? What's it actually going to take to build a device that looks anything like that? So, okay, fast forward to now, and there's a whole range of applications which have been developed for quantum computers. So really things that are quite established are algorithms, say, chemistry, material science, precision measurement, and cryptography. What's really emerging at a breakneck pace in the last few years are algorithms in optimization, energy storage and transport, machine learning and AI, and drug discovery. If you want to see like a full list of all like the rigorously demonstrated quantum algorithms, go check out the Quantum Algorithm Zoo. It's an amazing website where people have actually gone through and like exhaustively, explained all the quantum algorithms that have been invented and comparable runtimes and what the complexity of them is as far as we can tell. So go and check it out. All right. So far I've been talking about quantum computing for, a good 15 minutes now and haven't actually really talked about what it actually is. So here's an example of a quantum computer. So this is an example of a quantum computing architecture being developed at the University of New South Wales as part of the Centre for Quantum Computation and Communication Technology. This is an example of a silicon-based quantum computer. The qubits are basically built around phosphorus-doped silicon systems. I won't explain too much what the qubit actually is. It's a bit complicated in this architecture, but nonetheless, like you might be able to see from the picture up there, the qubits are really small. That's 200 nanometers, and they're all the way in there. And the big advantage about this particular architecture was that the interaction scale is like on the order of like 100 to 200 nanometers, which is like amazing because that's really long range for a silicon-based qubit. And there's a lot of computer science theorists here who understand what I mean when I'm actually talking about distances. Like that's really, really small. Like the smallest wires you can make on the order of about 10 nanometers. So to be really super happy about it being 200 nanometers interaction is like awesome. Anyway, so this architecture is an example. I won't go through it too much because this is like a planned architecture, not a thing which people have actually built yet. But roughly the idea is that you have these phosphorus. The purple things are phosphorus, implanted phosphorus ions, and like they interact over. This is what they call a flip-flop qubit. They interact over a I forgot the name of the interaction, based in electrical dipole interaction across the qubits. And these yellow things here are the idea that they were having is that potentially you could also interact qubits over long range through microwave cavities in these systems. Okay, but that's just an example. There's many, 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 many examples of quantum computing architectures. So let me try and summarize some of those. I like to think of these as basically generations of qubits. That's not saying one is worse or better than the other. It's just in terms of like which ones came first and gradually how things have changed. So people have been working on different types of quantum computer architectures for 20 plus years now. And the reason why they're working on different types is because all of them have some drawbacks and all of them have some advantages. And people are trying to develop new things to knock off as many of the drawbacks as they can. Okay, they don't always succeed, but they try, and that's cool. So the first generation basically was ion traps. So the reason for that is because we were really good early on at controlling at trapping ions and controlling. That was one of the first quantum control technologies that the world got really good at. So people were like, okay, let's build a quantum computer out of that. That was kind of the first clear example of a quantum computing architecture. There's issues with ion traps. One of the issues is like the actual speed at which you do gates is really slow, like way slower than my classical computer. So that's a bit of an issue. Clock speed is not necessarily a determining factor for how good a quantum processor is, but you don't want it to be really slow. That's a problem. The other problem is like it's really hard to put a lot of ions in a trap, interact them. So the biggest ion traps I know of, at least they've tried to do quantum computing on anyway, is like in the order of 100 ions. That is not enough, like nowhere near enough. So you've got to find ways of like joining ion traps together over long distances or like combining these things. So that's the whole thing, and many, many people work on that. Go and read about it, okay? Oh, so they're also big, I should say. They're actually quite big. They're not like on the scale of nanometers, they're on the scale of like millimeters. You can see them. So that's a thing, too. So if you wanted to build a really big computer out of this, it's going to be really, really physically large. Okay, the second generation, sort of the next ones that came along, were sort of diamond dots, So using like nitrogen vacancy centers in diamond, superconductors, and linear optics. So the first generation of superconductors and the first generation of linear optics qubits. Almost all of these technologies have the advantage of which the actual physical speed went up. The footprint went from being really small to being pretty big. So in optics, like integrated optics, which is kind of the small version of optics, it's still, you can see the features on a chip, like with your eye. They introduced the idea of with superconductors, you need to introduce like really cold things. To make superconductors work, it needs to be really, really cold. So, you know, we started looking at like dilution cooling. So a dilution refrigerator is like basically an amazing refrigerator that can take you down to like the order of 4 millikelvin. So that's really, really cold. And to do this requires a lot of work and a lot of energy to do this. And again, you're restricted to cooling down things of about this big, which is not very big in the scale of like how big. I mean, as far as I know, this is about as big as it gets for the staging of a quantum processor. So that's an issue. The third generation is kind of the things which are really emerging now. So over the last few years, which are variations on technologies which have been out there for a while. So some of the really interesting things are like diamond dots and variations on those diamond dots. The sort of second generation of, well, the first generation of silicon qubits that have actually been really demonstrated. Sort of new generations of superconducting qubits, like the transpond qubits and X1 qubits that Google uses. Again, speed's gone up. The logical speed, differentiating between physical speed and logical speed, I'll get into that later. The footprint has gone a lot smaller, so the chips, especially the superconducting chips, and the silicon chips especially, are now getting a lot smaller than they used to be. Now, the drawbacks is, for a lot of these technologies, they're all using some form of dilution cooling. So they all really have to be cooled down to make them work. Okay, and then the fourth generation is things that don't really exist yet. And sort of the main example is topological qubits, and that's what Microsoft's working on. If you go look at topological qubits, probably the first thing you'll see is a Microsoft website talking about that. The reason why topological qubits are really interesting is that basically they're using different phases of matter, which hopefully have inherent error correction abilities. So that's a thing people work in designing, but the problem is they're really exotic. They haven't really been experimentally demonstrated to the degree which you'd like to see. And basically, we don't really know, what the future is with those so far, because it's really, really experimental. Okay, so here's a bit of a snapshot of all the companies that are working on different things. So if I'd done this talk like 3 or 4 years ago, like it was all universities doing this, and now it's like companies. So ion traps, the really big efforts are IonQ, which is in Maryland, Alpine Quantum Technologies, which is in Austria, and NQIT, which is in Oxford. Color Centers and Diamonds is a company called Turing working on that. Superconductors, the really big guys, are sort of all in superconductors. So Rigetti, which is a big startup in the Bay Area, IBM, Google, Intel, and then you have QCI and QTech, which are like university efforts. Quantum dots are worked on by HRL Labs, which is a defense contractor in the US. Silicon spins, it's kind of the big thing in Australia. The Center for Quantum Computation and Communication Technology does that, and Silicon Quantum Computing, which is a spin-out company out of the CQC2T. Intel and QTech also work on this. So QTech is in Delft. Linear optics and silicon, there's a company called PsiQuantum in Silicon Valley, which is really big and kind of in stealth mode, so they probably don't let me talk about that, but they're in the Silicon Valley, and you can look them up. And anionic or topological qubits are done at Microsoft, primarily. Okay, so that's all neat, but why don't we have quantum computers yet? And how hard is it to build a quantum computer? So you might have got a sense of what I was saying, that like actually building like qubits is really hard. Like you need to really push the limits of what we can do in physics right now to just do that. Now, the biggest quantum processors we have now are ones which are in development. We don't even have real data yet on how well they work, but the biggest ones are at Google and Rigetti and reportedly at IBM. So they're on the order of 50 to 100 qubits, okay? To actually have a quantum computer work in a way that is tolerant to the noise, which happens in a quantum system, you need millions of qubits. So that's a thing. Like, it's a really big difference. And the reason for that is, well, there's two things. The first reason is that actually isolating quantum systems is really difficult. The thing which makes quantum computers really powerful as a computing model is the way in which they interact with, you can make the qubits interact and perform gates. That same effect, this is the fact that you basically can have entanglement across these systems, also causes you to potentially couple to things you don't want to couple to, which causes noise. So we have to work on this weird regime where we both want to make our logical register talk to one another, like we want our qubits to be able to talk to each other, to perform gates and to control them, but at the same time, we don't want them to talk to anything else. And that's a really hard thing to achieve, okay? Nonetheless, you can do it, it's just really difficult to achieve. So you need to do that, and then you scale up really big. Well, in the process of doing this, so unlike a classical computer where the error rates are extraordinarily low, these effects mean that we expect that, in the best case, if you go to an experimentalist, like the best fidelities people achieve right now is that you have an error rate of around 0.1% in your gates or your qubits, and that's really, really good to achieve. Experimentalists are very, very proud when they tell you that they achieve that sort of error rate on one of their gates. And then when you explain to them to actually build a quantum computer, it probably needs to go down another order of magnitude. They just want to walk out of the room and not talk to you anymore. So as a theorist, you encounter this quite a lot. But the reason for this is that, and that's still incredibly much higher error rate than the sort of error rates that you get on a classical computer. Okay, and so in order to really do computations of a large size, we need to go to another step, which is introduce something called error correction and fault tolerance. What that basically is a way of building redundancy into the way in which you build a quantum circuit so that you can be fundamentally resilient to noise. So when an error happens, there's a way of identifying it and removing it. Okay, and that actually requires really big overheads at the moment. So let's talk about what we actually need. Okay, so this is the sort of chart you get to see a lot at conferences nowadays. People talk about cost and value of algorithms. So let's talk about where things really are at. So where are we now? We're there on the scale of things. Where we want to be is over here somewhere, or at least people who want to make a lot of money in quantum computing want to be over here. If we really want to challenge classical computers, that's kind of where we need to get to, okay? So where we are now is what people call the NISQ era, which is a noisy intermediate scale quantum processor era. So that's that bit in green. And right now, people are searching to find applications which actually work. Okay, so once we get sort of beyond this, we begin to hit this sort of regime where we can begin to really do error correction in a meaningful way, and then things get a lot easier. So, I've drawn the exponential here like it gets much worse, but actually once you get to this scale, the technologies that are going to get us from here to here, if we can get to there, I don't see why you can't just sort of keep going. We will have mastered so many things at that stage, then this seems intimidating, like it's going to get worse and worse and worse. But actually, if we can get to there, my guess is we're kind of done. We've actually developed the technology which allows us to keep scaling a quantum computer. Okay, so what are we trying to do? All the theorists out there right now are trying to do that. They're going to push everything as much as they can from that side to that side and to push down the qubit numbers that are required in order to demonstrate interesting applications. So let's talk a little bit about timelines and where things are actually at. So here's a potential near future. I've been using this slide for 3 years now, and I haven't changed any of the dates on it, which is a bit sad. All right, so where are we right now? We're in the noisy intermediate scale regime, and what is everyone working on? Well, when I say everyone, the theory people, because I'm a theory person. So the really big things are error mitigation. So if I have errors in my device, how do I deal with that? Is there some quick, cheap little trick I can do to get around this particular error? Say there's a particular symmetry in the noise, which happens a lot, and I'm doing a certain type of gate that I can if I don't do that one, I can do this one or something like that, and people are working out how to compile in the presence of errors in a sensible way without actually trying to correct the error. The other really big thing is about testable advantage of your device. So that's devising benchmarks or demonstrations which you can perform and test and sort of say to the world, look, this actually worked. That's amazing. The other really, really, really big thing is heuristics. So every day on the QuantPH archive, which is where all the quantum computing algorithms show up, there is a ton of papers suggesting new approximate optimization algorithms, quantum simulation algorithms, quantum AI and machine learning things. And these are all based on the broad cluster of heuristics. For most of them, we don't really have necessarily significantly strong evidence that they work, or they work more efficiently than a classical computer can achieve, but nonetheless, heaps of people are working on this to try and propose interesting things and to try and work their way through these things. For myself, as a person who's very theory-oriented, I see a really important part of our role is actually to develop methods by which we can actually, evaluate these sorts of proposals. That, to me, is like what a lot of the complexity theorists are beginning to work towards. So how do we take these heuristic things and develop ways of actually saying, actually, that's a pretty good heuristic, let's roll with it. Or actually, this one wasn't very good, let's probably throw that one away. Okay, so where are we? We're down here right now. So 50 qubits would be awesome. I think if a lot of people said they had 50 qubits right now, they'd be really happy. Google, if you go and look online, they'll talk about their Bristol cone chip, which is 72 qubits, which hopefully we'll be seeing public data on at some point soon. We've seen some preliminary data at the American Physical Society meeting in March. Hopefully there'll be more data coming in the next few months. Okay, but their fidelities that they're sort of reporting or aiming for are around 99.7%, or that's like a 0.3% error rate in their stuff. That's roughly where they're aiming for. If you can get to 50 qubits with that kind of error rate, you can do a few things. You can begin to think about like saying, actually, I have like one really good fault-tolerant qubit, or maybe two, depending on how you do it. Importantly, what my talk is mostly going to be about is that this is kind of what we begin to call the classical quantum frontier. That's the point at which we achieve, and I hate this word, and I will try not to use it too much in my talk, what they call quantum computational supremacy. So that's the point at which you can begin to define some applications which significantly outperform a classical computer or the best classical algorithms that we have for some nicely defined window, which I'll explain shortly. Okay, so once we get to a few more qubits, right, like we need to go from like the 50 to 100 to get into the hundreds, we can begin to build much more unambiguous demonstrations of quantum computational supremacy. So rather than just like working with the raw qubits to try and punch out the thing, you begin to build in some notions of error mitigation and also some notion of maybe more concretely being able to test these sorts of systems that you're actually running things on. I'll try and explain that a bit later. I'm being a bit ambiguous on purpose there because it's a bit tricky to explain. But also, hopefully, once you get into the probably above the 100 qubit mark, potentially commercially relevant applications might be developed. So the things which people are really, really heavily focusing on right now are things around quantum chemistry. So I don't know, there was a paper about 4 or 5 years ago where they were sort of saying, to do a meaningful quantum chemistry simulation was going to, it's efficient, but it was going to be like n to the 16 runtime or something crazy like this, and was going to require an absolutely insane number of qubits to run it. Those sorts of numbers now to have an actual meaningful quantum chemistry demonstration are now really more in the hundreds of qubits. Like, they've come down dramatically, and that's because the algorithms have improved, but also a lot more attention is being paid to the level of accuracy that you actually want to do this sort of thing. There's heaps of work has gone into that, like by a lot of people. Okay, so that's neat, but like I said, we need to get into the millions. Okay, in order to get there, we need to keep improving the fidelities, so that's decreasing the error rates as we go, and find ways of scaling from like 50 to 100 qubits to thousands, and then tens of thousands, and then so on. And there's there's a lot of ways people are approaching to do this, but there are very few, how do I put it? If you put one of the leaders or one of the really big experimental groups up here and said, how are you going to get to 10,000 qubits? They'll say, I kind of know how to get to 1,000. And then it'll be like, well, maybe we can find a way of like connecting these things and then seeing if we can go bigger. It's a significantly challenging problem. The problem is actually a physics problem, more or less. Some people tell you it's an engineering problem. I think it's kind of a bit of both. So some of the really clear things we need to do is to work out ways, for instance, of making superconducting modes talk to optical modes, and that's really, really, really hard to do because they operate at very far distinct regions of like the energy spectrum. So this is the thing that people need to work on physically. Okay, so that was like the big introduction. Things are now going to get a bit more technical. So if people don't want to hear about technology, you just go, it's fine. Like that's the whole big, snapshot thing. Now let's get a bit more serious. Okay, so the first thing I want to talk about is a thing called quantum advantage. If you go online, and you would have seen a lot of talk about quantum advantage as being a thing. So the aim here is to find a quantum algorithm that is provably faster on a quantum computer than a classical computer. Okay, but that's for a specific algorithm. So this is the thing we want to do and like show that I can do it faster on my quantum device. What does that mean, for instance? Say there's a great, an amazing breakthrough a couple of years ago when Bravi, Goss, and Koenig proved that a problem they call a 2D hidden linear function problem can be solved in constant depth with a quantum circuit, but requires at least log n depth classically. So that grey line is the quantum runtime. It stays constant for growing problem size, whereas the classical problem requires log n runtime. Okay, so let's be clear. Log n runtime is something my classical computer can do. Like, that's not a huge improvement. This is not a problem that actually, like, you wouldn't build a quantum computer to solve this problem. But that said, doing that would actually be kind of cool, because you've actually shown that you've actually developed a processor that is capable of beating a classical processor for that sort of thing. And it's a pretty neat demonstration of actually that your quantum computer is working the way you hope it would work if you could actually do that. Okay, so that's an example. There's been a bunch of improvements. I'm actually missing a few there. That slide's like a few months old. There's been like 3 improvements on that in the last 6 months. I'm going to talk about another notion, which is actually what most of my talk is going to be about, which is this notion of quantum computational supremacy. It's kind of a different beast. So the aim here is to perform a quantum computation that cannot be performed classically in any reasonable amount of time. Okay, so it's quite a different problem. So there are some really big issues here. The first one, which is the gigantic elephant in the room, is that our quantum computer is super polynomially more powerful than classical computers at all, full stop. Okay, so we're now walking into the regime of complexity theory. For those of you who studied any complexity theory or know much about algorithms, it's all sort of dependent on a giant stack of cards, right? Like, so we end up proving things unambiguously in complexity theory, especially in the regime of super polynomial speedups between different complexity classes, is incredibly difficult to do. So if we were able to prove unambiguously that we had a super polynomial speedup for any application in quantum computing over classical computing, then we would have separated P from P space, which would be huge. That would be like the biggest result in computer science in the last 80 years. It would be gigantic. So we're not doing that here, unfortunately. The best we can do is prove these sorts of things relative to some reasonable conjecture. And that's what we will be talking about today. Okay, so issue number 1, better ways of separating complexity classes. That's a big issue, and we're going to talk about that. 2, for which sort of problems do the actual runtimes really radically diverge? What are the properties of the sorts of problems where a quantum computer really does significantly outperform a classical computer? And finally, can we do any of this without fault tolerance? Now let me talk about this slide. I haven't actually talked about the big graph in the middle of the slide yet. Okay, so if you have a quantum computer and you're not using error correction, the bigger the quantum computer that gets, the more noisy it gets. That's just what happens. As you add more and more qubits, the noise will get worse in the device. So when you run a thing on a bigger device, it just gets worse. The longer you run a quantum computer for, the more noise you'll get. You'll have like an error, say you had an error rate of like 1% per gate, like with every gate you perform, that error rate is going up, corresponding to the number of gates you performed. Okay, you do 100 gates, you're looking at like a pretty bad error rate at that point. You're definitely going to hit an error with high probability. Okay, so the maximum quantum runtime in a non-error corrected device goes down, like as your device gets bigger. So it looks like that. Unless you have a very, very, very well-crafted algorithm. Okay, so the sorts of applications we're looking for is something where the quantum runtime is really, really low. Say log depth or something like that, something really, really short. Whereas the classical runtime needs to explode and go exponential in order to see these sorts of things. So what we're aiming for is an application where that explodes, that stays, reasonable, and we manage to get under that red line somehow. So that's the sort of application that we're looking for to sort of demonstrate something like quantum computational supremacy. Okay, for any such application, if you find one, there's a whole bunch of things we need to do. You need to minimize the gate and qubit count, understand the influence of errors, mitigate those errors, and then improve the classical algorithms for attacking that problem. And that's exactly what I'm going to talk to you about. But first, we need to explain what quantum computers are. So I'm kind of stoked in that I've got like 35 minutes through this without actually really, in any way, talking about any math. So sorry, now it's going to get really mathematical really fast. But okay, so step 1, let's talk about qubits. Qubits are like the information carrier in a quantum computer. Like a qubit is like the simplest type of quantum mechanical systems. It's a 2-dimensional quantum system. Okay, the standard thing is to write a block sphere. The block sphere can represent the state of a qubit. What is a qubit? It's like a representation of the state of a 2-dimensional quantum system, and the way you represent it is by a unit vector. okay, a two-dimensional unit vector. It's complex because it's nice to make it complex. It's handy. It doesn't actually have to be complex, but yeah, it helps to make it complex, just for efficiency's sake. Okay, a really important feature, well, the thing we talk about is measurement. So measurement on a qubit, a sort of standard measurement on a qubit anyway, is discrete and probabilistic. As this is a two-dimensional state, when you do a measurement here, it collapses the state into two possible outcomes, defined necessarily by opposing poles on the sphere. So an example, which is kind of easy one, imagine you would do what people call a Z measurement, or a Z-basis measurement. Like you get collapsed into either the 0 state or the 1 state when you do that measurement. Okay? This is kind of a weird thing. Like it's a fundamentally discrete thing, but this object is like, it looks continuous anyway. You know, it's a thing which is a surface. Actually, it doesn't have to be a surface, it's actually everything in the region of the sphere too, but we won't get into that too much. But the measurement itself collapses things. So that's sort of, maybe we're going to do this, it's going to get too philosophical, but it's a thing. And it's a little bit weird, and this is where a lot of the weirdness in quantum mechanics comes from. I shouldn't say weirdness, it's not weird. It's just the way it is. And, you know, quantum mechanics is fundamentally a theory about, like, how we can access and describe quantum systems in nature. In and itself isn't like, it's not a theory like electromagnetism, which actually seeks to describe the forces of nature. Quantum mechanics is a framework that we use to describe nature. So, all right, so measurement happens, and when you do a measurement, like a measurement happens probabilistically, and that probability is defined by the inner product between the final measured state and the initial state that you began with. So it's literally computed as an inner product. And you can see that, well, it's a normalized unit vector, and this is probably measuring a state given by this. Okay, and it's literally the inner product of those two vectors. We call that inner product the amplitude for a measurement. So dynamics, which I'll talk a little bit more on the next slide, are defined by operations on the state. This is a two-dimensional vector, so we just apply 2 by 2 like operators on that vector, or matrices on that vector, and that's sort of the way in which we update the dynamic of this sort of thing. Normally, at least in quantum computing, it's mostly unitary matrix is what we talk about. And finally, the state of an entangled qubit, like an isolated qubit, which is nonetheless entangled with other things, is dependent on the states with which it's entangled with. But if you want to look at that state on its own, it's represented by what we call a density matrix, which is a probabilistic mixture of what we call pure states. And that was a pure state up here. Okay, I'm not going to go into that too much more. That was just a thing, just so you know, for completeness. I like angsted over whether I should say that or not, because it doesn't come up too much. Okay, so let's talk about many qubits. That was one qubit. What does many qubits look like? So imagine all these vertices are qubits. The state of an n-qubit system is a 2 to the n dimensional complex unit vector. One way of writing it would be like this. It's a sum over 2 to the n different combinations. Each one of those x's labels a basis state for this vector. And the alpha x's are just complex numbers, you know, indexed by x. You know, here's the question, how do we even write that down? Okay, for a really large n, how do you even write that on, you know, in any way? Can I make my computer write that down? Well, so we don't. And this is one of the magic things about quantum mechanics. They don't really tell you when you're undergrad. So one of the tricky things about quantum mechanics is that, you know, you learn this formalism, and that's neat. What they don't tell you is that there's some hidden cute little facts. One of them is the thing that we actually write down is the Hamiltonian. So you learn all about Hamiltonians and that, but you don't learn that there's this fundamental disconnect between the way the state evolves and the fact that the thing which is efficient that we can think about is the Hamiltonian. And that's the thing that actually sort of governs the physics of the system. Okay, so we describe a Hamiltonian or energy operator that describes the interactions between qubits. Usually this has a polynomial size description. This is why we can actually do stuff. Okay, so my example here is the Ising model. In the Ising model, what you have is, I'm not going into what it is too much, but like basically in a lattice, it's the Ising model, for those who don't know, it's a model of magnetism. It's sort of a rudimentary model of magnetism that people invented way back in the statistical mechanical days, and you can make a quantum version of it, and it looks like this. Anyway, you assign weightings to each of the edges. The weightings are just like real numbers that you assign, okay? And you have a magnetic field strength, which is assigned to a vertex, and then you have these operators, Zi, Zj, and we so they're Pauli Z operators and Pauli X operators. That doesn't matter too much. You don't need to know what that is too much here. but you can write them up. If this is on a lattice, there's like n squared, order n squared operations here. Okay? There's order n squared things required to describe this. Okay, the dynamics. Okay, the thing which like governs the way the state of the system changes are determined by the exponential of h. And that comes from Schrödinger's equation. Okay, it's given by that thing there. Okay? That's where the magic happens. The magic happens is this operator, the EIHT. That's a really big matrix, actually. And working out what the matrix entries of that matrix are is actually quite difficult. Okay, and the probability of measuring any given x is given by the amplitude with regard to that state x. So it's the overlap of that state with that x. Okay? And that's kind of where all the magic happens in quantum computing, and that's where we're going to go. Okay, if you want to learn about quantum computing and just have a bit of a feel for how these things work, I highly recommend, if you've not done any of this before, going and Googling Quirk and Craig Gidney. And Craig Gidney is the software engineer at Google who made this really neat little visual drag and drop quantum computing simulator thing. So in a quantum computer, so what I talked about there was a quantum system. What a quantum computer is like the dumbed down generalization of what a quantum system is, basically. So those interactions I was drawing are gates, okay? So what we're thinking of here is having like a whole series of small, of evolutions on a given state. So over here we have the starting state, and then we're applying an evolution, like one of those unitary operators, and another one, another one, another one. And that's what all these things are, okay? And it's a polynomial size, well, for an efficient quantum computation, it would be a polynomial size list of all of these operators. Okay, but anyway, go and play. Here's a video I grabbed the thing, and like over here, that's the matrix, which is implemented by this circuit, and how he's sweeping over the possible inputs here. And so you can see that this thing is changing around like crazy. It's kind of cool to play with, actually. So you can drag and drop them, see how these things change. Anyway, it's cool. I just wanted to advertise it. Craig did a really good job of doing that. It's all open source and free and whatever, so you can go on there and Google it and play with it. It's a whole bunch of really good examples. Okay, so let's do what a quantum computer is. Like I just sort of roughly explained it. I'm going to be a little bit more formal now. So, okay, the input is a classically easy to describe circuit U, an input state, which is really simple. Normally just say it's the all zero state. It's something you can prepare easily, or you should be able to prepare easily if you have a model of quantum computing. U is comprised of polynomially many gates from a finitely defined gate set. A classic example is something called the T gate, the Hadamard gate, and the control Z gate. There's a lot of them, but it's a simple, easy to describe gate set. It's not, importantly, it's not continuous, okay? It's finite and finitely representable. A universal gate set, which is a term you'll hear a lot, are gate sets have the property they can simulate any unitary, assuming arbitrary runtime and ignoring errors. And the output is another really important feature. It's literally just strings of bits that occur with probability given by the measurement update rule, the measurement probability rule. So it's just given by the overlap of U with 0 on the bit string, or the vector representing the bit string X. Okay, there's some really important facts you need to know and think in your head, and they're not sort of stated enough. A quantum computer does not compute its output probabilities. It's not a thing it does. The output probabilities define it, they're inherent to it, but it doesn't compute them. What a quantum computer does is spits out ones and zeros. If you want to know what the probability of any one of those sets of ones and zeros is, you actually have to infer it somehow from that probability distribution. Or you need to write an algorithm that somehow tries to compute it. Okay? It's not given to you for free. So we have this incredibly complicated object. So this 2 to the n by 2 to the n unitary matrix, right, which can be very complicated to work out. It's defined by the circuit, but we don't necessarily get to read it out. So reading it out is actually a hard thing to do. Okay, for an arbitrary polynomial size unitary, this means we can only ever estimate R of x to like within 1 over polynomial precision, generally. And that's almost like the definition of the complexity class BQP, which is bounded error quantum polynomial time decision problems. Okay, whatever. It doesn't really matter too much for this talk. In general, fault-tolerant quantum computers can only be guaranteed to produce samples from some probability distribution R of x, such that the difference between R of x and P of x in like variation distance, for instance, is like 1 over a polynomial. That's kind of what we get guaranteed in general. I mean, there are some exceptions to that, and there will be exceptions to that, but in general, that's kind of what you get with fault tolerance. So when you're designing a quantum algorithm, that's kind of what you're punching for and showing that it works up to those sorts of error bounds. Okay, so let's talk about the actual topic of the talk, and not just quantum computing. So, let's talk about the problem called random circuit sampling, which is the prototypical example of like a quantum computational supremacy experiment. The goal here is to output samples x with probability p of x defined by a random circuit. Okay, why is this interesting? So the idea here is to bound the complexity of sampling via studying the properties of p of x. So the hope of this whole idea was that if p of x is complex enough, then classical computers can only ever simulate sampling by actually computing p of x. That there isn't another way out, which allows you to not have to compute these functions. Okay, so why random circuits? The intuition is that random circuits quickly develop long-range entanglement. So for every qubit, there's a lot of dependencies on all the other qubits in the system. Okay, that's the idea. And that these dependencies will be subtle if you randomly choose the gates. This, in principle, should make them among the hardest to simulate accurately for sort of, well, they definitely are among the hardest to simulate classically given the known sort of algorithms we have for computing output probability distributions from quantum circuits. All right, so the first really amazing example of this was given by Aronson and Arkhipov, and it's a paper that's called the boson sampling problem. There they established a potential advantage over classical computing for sampling random linear optical networks. Importantly, the advantage holds for this problem of approximate sampling. So it held when you actually aren't guaranteed to exactly have what you've defined mathematically on paper. And they ruled out any efficient classical algorithm from outputting samples assuming, well, 3 conjectures, and 2 which are sort of, well, 1 which is probably almost certainly true, and 2 which are still open. The first one that is almost certainly true is that there's a thing called the polynomial hierarchy, and that doesn't collapse. So that's an object in classical complexity theory. Like, we're pretty sure it doesn't collapse. It would be a big deal if it did. Like, a lot of computer science is going to change really quickly. The other 2 open conjectures, one is about the average case complexity of the permanence of Gaussian matrices, and the second is about the randomness properties of those sorts of permanence. I won't get into that too much at all. So the work that we did was what people call IQP sampling, and this improved on boson sampling by proving the equivalent of what they call the permanent anti-concentration conjecture for IQP circuits. And it's defined in the quantum circuit model. All the other big improvements is defined in the quantum circuit model and yields very low depth circuits. It also allows the usual machinery of quantum error correction to apply. So this would also apply in principle, without any of this trying to do it in the near term. It's the thing that you could actually do if you had error correction. And also it could be easily generalized, and the generalization is actually kind of the important thing here. So basically we took down something that had 2 conjectures is now 1. And that one conjecture I'll get into later, but it's essentially that the average case complexity of certain families of combinatorial problems are as hard as the worst case complexity. And I'll get into that as we go on. All right, so the most notable generalization of this is what people call the Google proposal. So the Google proposal is essentially we're going to perform random circuits, okay? So the way it's defined is that we have a 2D lattice, and then you apply basically a series of Hadamard gates. I haven't said what a Hadamard gate is. What a Hadamard gate does is create a big superposition over all the possible input states. So it really goes from being like one vector to being a thing which has like weight over the entire of the helper space. Then you apply a series of entangling gates, like 2-qubit entangling gates, a series of single-qubit gates, a series of 2-qubit entangling gates, and so on. So you build up a big random circuit, essentially. So there's a bunch of details, like the proposal we actually put forward had to be a 7x7 array of qubits as a minimum. It needed 40 layers of gates, each with an infidelity, so an error rate about 1 on the circuit size. In that paper too, we introduced this notion of cross-entropy benchmarking to validate these sorts of things. But really importantly, we also did tons of numerical testing to certify the level of randomness in the circuit, which is required for technical reasons in the proof, for benchmarking, and the point at which these circuits become really hard classically. Okay. Oh, right. I should warn everyone. We're about to get a bit more serious about the computer science now. I've been playing with kid gloves, but now to get a bit more real. Let's talk about the complexity of computing and output probability from a quantum circuit. Okay, so like I said a couple of slides ago, the goal here is to bound the complexity of producing samples by the complexity of computing an output probability. So since the beginning of quantum computing, we've known that exactly computing the output probability from a quantum circuit can, in the worst case, be gap p hard. Okay, what is that? So gap p is a counting class. I don't know how many people know about counting class, but like it's a thing that takes as input how do I put this? An NP, well, it takes an NP machine and says, okay, I'll say this a bit more simply. Imagine you had, a poly-sized classical circuit. Your goal is, or a Boolean function. The goal is to say, okay, tell me how many inputs evaluate to 1, right? So that's the prototypical example of a counting class. So sharp P is defined that way. It's written up there. Gap P is the generalization of sharp P that allows negative numbers. So it takes the difference of these things. This seems totally trivial, but is not, which is what's weird. So that's the thing when I learned about this, I'm like, really? That's different? Why would that be different? The difference is because under approximations, these two classes behave differently. So these numbers can be very subtle, right? So you can have a difference of like 1 over 2 exponentially big numbers. Under approximation, taking the difference like this, depending on the type of approximation you have, can lead to like wildly different answers. So imagine you had 2 sharp P things, you get an approximation to a sharp P function, an approximation to another sharp P function. You want to like take the difference of them. Depending on the type of approximation you have, you may not be able to get an approximation to a gap P function, at least to the same level of accuracy. Anyway, that's one thing. So gap P functions have the property that under relative error approximations, so a thing that looks like that, they stay gap P hard. That's the property of gap P hardness, or gap P completeness. Okay, so these things are sort of at the heart of quantum circuits. Okay, these things have these properties. And as I said before, if we wanted to like get an additive error approximation to one of these things, what you actually get out of running your quantum algorithm, the best you can sort of hope for is a 1 over polynomial additive approximation. This is vastly different to this. If you only have a 1 over polynomial error, is the best thing you can achieve. The range of these functions is like exponential. So they go from 0 in increments of 1 on 2 to the n up to 1. Okay? But if you only have 1 over polynomial accuracy, you're going to get like a horribly wrong answer if you try and infer what the answer is most of the time. So the only way that you get a good answer is if you know other properties about these sorts of circuits. Okay, so that roughly explains it. So this is way up here. In between here and here is like the entire polynomial hierarchy, which is an infinite class of generalizations of NP, which is distinct from P. Bounded error quantum polynomial time is like this blue blob down here. You have the quantum generalization of NP, which is this red blob over here. I don't know if you can see, NP's there, classical efficient computations are in here, factoring lives like there. Okay, this is like where things are for quantum computing. All right, so how do we use this? So there's a really beautiful theorem that goes back to the early 80s by Stockmeyer. And he showed that actually, so sharp P is up here. Actually, P to the sharp P is up there, but never mind. Sharp P is up there. What he managed to show is that if you wanted to get a good relative error approximation of a problem in sharp P, you can actually do it inside the polynomial hierarchy. So you can do it down here. But this is in stark contrast, as I said before, to gap P. Gap P stays up here under relative error approximations. So, learning about complexity theory and things like this, but basically like when I learned about this difference in fact, this is the sort of thing where everyone's like, wow, actually that's a huge difference, surely we can use that. This thing is the heart of quantum computing, this thing isn't, can we use that somehow? And the answer is yes. So a series of papers have worked on this, but roughly all the arguments, so boson sampling, IQP sampling, all of them come down to the following statement. The quantum random circuit sampling argument is essentially that if there exists sufficiently accurate, efficient classical samplers for the outputs from sufficiently random unitaries, Stockmeyer's algorithm can be used to approximate the output probabilities of these circuits, which could be gap P hard. Okay? So what people have shown for a range of problems now that you can randomly choose certain families of circuits, feed the outputs through Stockmeyer's algorithm, and Stockmeyer's algorithm will give you a good relative error approximation to a large fraction of those circuits. Okay, so that's interesting. It doesn't tell you actually anything about complexity theory, because we haven't talked about how hard it is to actually solve that. So complexity theory is about worst case hardness, not average case hardness. This is kind of a thing. Okay, so imagine you had some family of quantum circuits where you can prove that computing the output probability, is gap P hard or say sharp P hard under relative error approximations in the worst case, okay, which is generally what we get out of these arguments. So that's a family. Imagine this big set. That's the family. The sorts of things that you can show is you can prove that they are sufficiently random. There's a technical term called anti-concentration. I won't get into that, which is a blue line, so a big fraction of them anti-concentrate. That guarantees that this Stockmeyer's algorithm actually delivers you a good approximation to things you've randomly chosen from that set. But the other ingredient that you want is that approximations to the output probability, on average, are also as hard as the worst case. So this is a situation one. So if you have both these things on reasonably large fractions of the things, you're guaranteed with reasonably high probability of having an overlap. And then this is great. Like, you've managed to show that, you know, quantum computers can't be simulated by efficient classical computers unless polynomial hierarchy collapses. Unfortunately, what we actually have is this right now. This is what we know in this sense. So we can prove that this anti-concentration properties holds for large numbers of things. We can prove the worst case complexity for these families of circuits satisfies the right requirements, but proving that the overlap happens is not where we're quite at yet. So what we need to prove is that on average, or enough of the P of X are as hard to approximate as like the worst case, i.e. they're sharp P hard. Now, actually, in the last 12 months, there's been some really big progress on this problem. So what people have managed to show is that you do have an overlap for the case when you have an exact output. Well, you have the average case complexity of exactly computing the output probabilities of these functions is as hard as the worst case, okay? So that was a big improvement over what was previously known. However, it's not actually sufficient, because what we need is that the approximation, this holds under the approximations as well, and that hasn't been proven yet. Sorry, that was a bit technical, and a bit hard to explain. And so I'd recommend you go and read the paper to have a look at that, because it is actually very, very technical. So what we actually want is the property of random, it's called random self-reducibility, okay? And random self-reducibility is a property that basically you can have a polytime algorithm on randomly chosen instances, which will output the output to a deterministically chosen instance of that set. Okay, so every gap P complete problem is randomly self-reducible. We know that. But the question is over what set, what randomly chosen set. Okay, so this is actually a technical problem. So you can do this for exact boson sampling. And as I said, last year there was a really great paper which showed this random circuit sampling in the case when you're actually delivered exact randomly chosen solutions. Still to be addressed is the problem of doing this for approximations. And actually, we know that this is likely to require non-relativizing techniques, which is complexity theory jargon for like it's really, really hard to solve. So go and see Aronson and Chen's paper from 2016 on that problem. All right, so like I said, there's this, what are the families of circuits? I've actually really talked about what the actual families of circuits are that have this property. There are actually quite a lot of examples now. Since we put out the first paper, there's probably been about 20 different families of circuits identified with the right sort of properties. So basically what people punch for is to show the worst case hardness. That's actually a thing which isn't too hard to show. Then you want to show that they've got the right randomness properties as well. And that's the property we call anti-concentration. So the general technique people have been doing to do this is direct calculation, which is what we did for the IQP circuits. It turned out to be not too hard. Using the theory of k-designs, which is sort of a generalization of, well, you should just look up what the theory of k-designs is. It's a bit hard to explain for this talk. Generally, that's what's been used for things like the Google proposal. And the use of measurement and post-selection gadgets to demonstrate anti-concentration on a subset of some output qubits. Okay, so the example that I've been talking about a lot is this IQP sampling example. Let me just walk you through like what the sets of these things look like a little bit. And then you don't need to understand too much about this, but we'll give you a sense of it. Okay, so an IQP circuit is called instantaneous quantum polynomial size circuit, okay? Why instantaneous? It's because it doesn't have much time ordering structure in the circuit. So here's an example of a quantum circuit. There's a bunch of Hadamard gates. Then all these gates in gold here all have the property that they commute with one another. Another way of seeing it is to say that if you were to write this in the computational basis, they're all diagonal in the computational basis. So that means that they can be like applied in any order, and it doesn't change the output of the computation at all. And then you have Hadamard gates at the end, and then you get a measurement. So that's why we call them instantaneous, because they can be applied in any order. They're a particularly simple class of circuits. They're very, very low depth in general. This lack of time ordering means that they're a low depth. And the sorts of, for this type of problem anyway, we can basically restrict to just thinking about random circuits of what we call T gates and square root of control Z gates. And what we managed to show is that the average case complexity of relative error approximations to either the complex temperature Ising model partition functions or the gaps of degree 3 polynomials, if the average case is as hard as the worst case for these problems, then quantum computers can't be classically efficiently simulated without a collapse in the polynomial hierarchy. All right, so I'm not going to go into the gap of degree 3 polynomials problem. Though this is a computer science audience, I probably should have led with that one. That's probably one thing people understand better. But here's the Ising model partition function problem instead. So draw a graph, as I explained before. Vertices are qubits, and edges are like interactions between them. Okay, we basically just choose a discrete set of edge weights given by, well, k pi on 8 for k from 0 to 7, and vertex weights given by L pi over 4 for L 0 to 3, and choose them at random and apply them to the thing, okay? That's a way of defining a graph and defining a Hamiltonian, which will be given by that thing. Then you can show that the amplitude, defined by this thing here, okay, is always proportional to what they call the Ising model partition function. It's actually the classical Ising model partition function. This is a very well-studied combinatorial object, which is known to be, well, in this class, gap P complete over this range. Now, the Google proposal, similar sort of story you can apply. You apply all these gates and whatever, but what you can actually do is to show that every single amplitude coming out of these circuits is proportional to a quasi-three-dimensional Ising model partition function as well. So you can use the complexity properties of the partition function in order to analyze the complexity of these circuits. Okay, so that's the complexity Ising model partition function in the worst case, but let's not get into that. That's a bit too much for this talk. But talk to me about it later if you want. So that's basically a classification over the set of potential inputs for the Ising model partition function, the worst case complexity of this. It's basically complete more or less now. All right, so I've talked about a couple of families in particular, the IQP sampling family, the random circuit sampling family. A really neat feature, which is identified by a series of authors, was that actually you can trade off time and space in these arguments. So the random circuit sampling argument was basically designed to be minimum number of qubits, maximum number of packing the gates in as much as you possibly can, to jumble up this state as much as you possibly can. But it's got little subtle differences, which are things you actually have to compute. What a whole series of authors have shown is that actually you can kind of unpack this and end up having like a deterministically chosen circuit from which you can show that this random sets of circuits emerge on particular subsets of the qubits. And then the overall circuit inherits the complexity defined by this subset of qubits. So you can trade off time and space in these arguments in certain ways via certain sorts of constructions. So this is actually kind of neat because actually instead of having random circuits now, you can imagine having deterministically chosen circuits. And the random circuit sampling arguments bound the complexity of the deterministically chosen circuits. So that's the thing a lot of people are playing with now. There's also a few subtleties about these time-space trade-offs. It actually gives you bounds also on the size of a simulation and the runtime of a simulation. So for the random circuit sampling argument, you can actually show, or for the IQP circuit sampling argument, you can show bounds on the minimum number of gates in order to achieve the complexity you require. And this actually invokes, it tells you basically how much these things have to scale when you trade off time and space. So for instance, if you were to flatten the constant depth, you know that there must be at least a polynomial increase in the number of qubits you require. Okay, all right, so that's really high-level stuff compared to what I'm going to talk about now. I'm going to talk about noise a little bit. So, all right, so I mentioned before that noise is a thing, okay? And all the statements, all the theorems I was talking about was within constant variation distance. But as I said before also, the number of errors in a quantum circuit increase as the size of the circuit increases and the size of the system increases. So then you might ask, okay, so how do I maintain a constant variation distance under those conditions? And the reality is you can't. You've got to actually use fault tolerance in order to achieve that. But like I said, you can hope that you can get inside those bounds for any given size of the circuit. But fundamentally, complexity theory is about asymptotics, not about constant size effects. So that's the whole thing. So this is what requires a lot more actual analysis. Okay, so something we showed a few years ago was that actually, if you were to even just use a very simple noise model, which basically just randomly flips bits at the end of the circuit. That's really simplistic. It's about the best case scenario noise model you can hope for in a quantum computer. And under that scenario, actually what happens, the distance from what you're aiming for diverges like linearly from what you actually have. Okay, so the bigger the circuit gets, the worse things get. Okay, so you're definitely not inside that concept I know about, but you might hope, maybe this is still hard to classically simulate. Well, the answer is it's not. And we were able to show that. So we showed a classical algorithm which had provably quasi-polynomial runtime for that kind of problem. Runtime is given by this, and it depends actually on how random the circuit is. So we use the randomness in this algorithm. It depends on the depolarization rate per qubit, the error rate per qubit, and the amount of error that you're actually going to have in the system. So, and the runtime is more like that. Now, it's a really steep polynomial, like really, really steep. And that's kind of actually a feature we should talk about. So let's talk about fidelity versus runtime. So the noisy simulation runtime, like, oh, and I should say that can be generalized to the Google circuit, and people did that. The noisy simulation runtime is given by this n to the order log alpha and delta divided by epsilon, which comes from the number of terms required to be computed to have these two probability distributions for the noisy things actually get close. Okay. Now, in order to maintain this constant total variation distance thing, which is like the first requirement for any of these things to be true, epsilon actually has to vary like 1 over n. If you throw that into the runtime, then you get like a runtime which is like n to the n, which is really, really bad. So for low error rates, the runtime of this algorithm is awful. And actually, the experimental goal is actually to do better than the error rate anyway, so that's not such a big deal for small size systems. Okay. There's a great paper by Sergio Boisho and others who showed further that, like, actually, if your goal is to go further than to demonstrate the distance between the uniform distribution and let me explain this more carefully. He showed that basically, in the cases when the runtime of this algorithm isn't bad, you've basically got a completely randomized just coin flipping process going on. So it's super easy to classically simulate. So you're literally just flipping coins in order to simulate what's actually happening in the circuit. Recently, there's some really interesting middle ground where people have been able to trade off fidelity versus runtime for these problems. And there's been a series of papers about that, and people use this now in evaluating these problems. All right, so let's take a step back. Where exactly is the quantum frontier, after all this I've been talking about? Okay, so it cannot be answered with asymptotic arguments alone. It actually depends on the amount of system noise, the model, and the best classical simulation algorithms. Tensor network methods are the best methods we had for doing these simulations, and they utilize symmetries in circuits and the noise model to reduce the complexity. So actually, what we originally proposed was around 50 qubits at depth 40 is about where it happens. That's roughly, basically, what seems to be bearing out to be true. Arguably, you can get a few more than 50 qubits, like 55 or something, but that's about as far as Manuel has actually got. For the sparse IQP problem, you can get to 60 or 70, and it's about 50 photons for this personal sampling problem. In the last month, actually, there's been an amazing paper where they've actually thrown this problem. They've used the Summit supercomputer, which is the fastest supercomputer on the planet right now, to evaluate this problem. And using the Google proposal as an example, they've basically compared what can be achieved with your quantum processor versus the classical processor. They take a bigger view of this, actually, and talk about like how much energy it actually requires to do the computation, as well as the actual runtime of this problem. And what they're able to find for this problem is that for the runtime hours for the Electro supercomputer, which is at NASA, was about 59 hours. So that is really big. On Summit, it was about 2.5 hours. On the quantum processors, it was like 0.028 hours. The energy cost, also accordingly, was like dramatically different. On Electro, it was in megawatt hours, it was like 96.8. Summit, 21.1. And for the quantum processor, it was 4.2 by 10 to the minus 4. So we're seeing a dramatically different runtime in using the best classical algorithm between what you achieve quantumly and what you achieve classically. So this is roughly about where things are at right now. Okay, so are we actually like looking at seeing like a violation of the extended Church-Turing thesis? Well, there's a hidden thing which I haven't talked too much about, and I don't really have time to now. Nah, maybe, maybe not. There's a philosophical argument. How do we verify that we even did these circuits at all? Okay, so there's a hidden thing which I've been kind of avoiding saying, which is that in order to verify that these computers did what you claim they're doing, we have to analyze the probability distribution. And we have to analyze them really, really, really carefully using a whole lot of computing power to do this. One of the reasons why Google and NASA did that calculation was actually for benchmarking the capabilities of their own processor. They needed to do those computations in order to build a hypothesis test that their devices are actually working correctly. So there's a weird fundamental disconnect where we can have a very complicated thing, and these particular things are chosen to be sort of maximally complicated, but we also, at the same time, inherit sort of a maximal complication in the verification of these problems. There's actually a way out, and I won't get into that, but I'll talk to people if they want to ask me about it later, which talked about how you can do quantum circuit verification via a whole bunch of really cool cryptographic methods. And I should point out the problem we actually want to solve here is not what is the probability distribution output by this circuit, but rather did we do the circuit or not? And that's a subtly different problem. So I'm going to skip all of that. There's a whole bunch of cool stuff about that. Finally, okay, how hard is it to develop near-term quantum algorithms? The problem is really hard. So Rigetti Computing, which is a startup in the Bay Area, have put forward $1 million prize for the demonstration or a quantum algorithm which actually can be performed on a near-term device, which actually has some real utility. Recently, in January, Airbus actually put forward a whole bunch of challenge problems as well, which they're challenging people to develop algorithms for those specific problems. I'm not sure how big their prizes are. It's a bit ambiguous, but yeah. They're basically putting forward cash prizes to solve these problems. And it's really important to think about when you're evaluating these things. The problem is not just a complexity theoretic argument. We really need to know, can you actually legitimately do it faster in terms of the amount of man hours and computing hours required to solve the problem? If if I have a particular problem which I can solve with almost no thought on some code I knocked up in 30 minutes on my quantum processor, is that outperforming an incredibly hard optimization which I required a grad student from MIT to solve at a cost of $1 million a year? This is actually a thing which commercial companies tell me that they actually care quite a lot about. And this other question, is it more accurate, and is it ultimately more cost effective to use a quantum computer versus a classical computer? And I guess these are the things that the community is now, up against and trying to work out. Okay, so thank you for listening.
Any questions? Steven.
Thanks for the talk. The last thing you touched on was this verification problem, which comes up, I guess, in quantum computing. But why doesn't it come up classically? Why is there not a classical verification problem?
There is, but we don't talk about it.
Right.
So this is the thing. There definitely is. So if you're doing machine learning problems, right, there's a problem there of verification, fundamentally. So we don't really know that you develop your machine learned model. You don't know for sure that it actually is the model. It's just an approximation to the thing, right? And actually doing the full verification is as hard as the learning problem in the first place, right? That's what we're actually doing. So yeah, the problem emerges that way, but it's particularly pronounced for this quantum supremacy argument. In general, many problems in BQP, this isn't a problem, because there are actually many problems like factoring is inside MP as well. So you've got an efficient certifier, and it's really easy. And I should say, this work by Mardev shows that there is actually a way of running these problems such that you really can have a verifiable implementation of any quantum circuit. That's was such a huge breakthrough, subject to the learning with errors problem actually being hard for a quantum computer. Okay.
When I saw your slide up there about, first, second, third, and fourth generation, and then on the first slide, the first generation, I thought of the word factor, and in my head, I thought of 0.0. Does that play a factor in generation 4?
Sorry, so you're asking about the vacuums. What do you mean by 0.0? Could you elaborate?
Well, like creating a vacuum at 0 degrees.
Oh yeah, so for those ones it's not at 0 degrees, but for a lot of these problems we want to get it almost at 0 degrees to make this work. So in order to see the quantum effect, for instance in superconducting, you need to get it really, really cold. And to maintain that, when you have a lot of these qubits interconnected, you have to keep it really cold. That's totally a thing. So you have this transition from the phase of matter being one thing to phase of matter being another thing, and that's the effect we're actually using. Okay, thanks.
How is quantum computing applied in energy storage?
Oh, so actually, the reason I put it up there is I went to a great talk last week about this. So people are working on, there's a paper, people are working on developing better batteries, essentially, using quantum chemistry algorithms. So people are developing, have adapted various algorithms for analyzing catalysts and things like this in order to actually develop better batteries. So there was a paper by Google and Daimler about this, like about a month ago, who are working on this. So Daimler's an auto manufacturing company. This is a big deal for like cars, Tesla, everyone who has like fancy batteries, like they want more efficient batteries.
Yeah.
And solving this problem requires computing hard problems in chemistry in order to do this. And so people are working on that pretty actively, actually.
In terms of noise, right? So it's something that will get better with advance of technology, or is intrinsic with the
Okay.
quantum?
It's definitely, so noise is definitely intrinsic to every quantum system. It's really hard, as I was saying, to strike a balance between being able to control a system and to isolate it from things you can't control. So if you want to be able to control it, you sort of open the door to being able to do things to it. But when you do that, like you're also opening the door to other things interacting with it. So you can have qubits which last for 10 minutes. People have shown that. So you can encode the state in a thing and leave it and walk away. So that's the thing you can do, but those qubits don't interact with anything. So it's pretty hard to make them to make gates out of those devices. Yeah, so it's this weird balance. So but that will get better. And like I said, but at the moment, it seems like we actually really do need to go to using fault tolerance to actually ultimately beat noise. But, hopefully I'm wrong about that. Hopefully Microsoft builds brilliant topological qubits, which I don't have to worry about these things anymore.
And they will put the Windows on that.
That's right.
Any more questions?
Yep.
Have you ever been down, perhaps in my lifetime, then in your lifetime, when the PC would write sort of down shops for a couple of qubits in it?
Well, a couple.
Bravo.
Well, yeah, so I'm okay. I'd be really amazed if we have a quantum processor in a device that we have that we can access all the time. I mean, let me log into quantum processors now. Like you can go to the IBM Cloud Experience, like on that computer, and run a job on it. Like we could do that now, basically. Then it's not a very good quantum processor. It's got a lot of noise in it. In terms of actually using quantum technologies to do things more realistically, I guess the prototypical example people give is quantum cryptography. So the idea is you could do key distribution. People claim that they're doing that now as a commercial product. I'm not sure if it's really a thing that you want to get into as opposed to doing classical crypto, but it's a thing people claim you're doing now. But yeah, in terms of like easy to access quantum processors, which actually are really good, I don't know if I'll have it on my desktop for a while because they're really big. But certainly within the next 12 months, maybe 24 months, you'll be able to access pretty good quantum processors which can do things which are non-trivial via the internet. Like that'll definitely happen in the next 24, well, I shouldn't say definitely, very likely to happen in the next 24 months.
In terms of, for, let's say, programming or writing programs,
Oh, cool.
what's going to happen?
Okay, so like I totally was going to prepare slides on that and then realized I had way too much material. So actually I was just at a workshop last week on learning how to use these new software environments which we're using in our teaching going forward. So people are developing software environments or rudimentary programming languages for coding up quantum computers. Google has one they call Circ. Microsoft has a more sophisticated one called Q#. And these are things you can play with, yeah. And Q# is like a bit more full on. So Circ is really designed for near-term devices. So like the way it's designed is that when you're programming the thing, they absolutely expect you to use the quirks of the device. And it's designed to force you to do that. Q# is abstracted away a bit more.
All right.
So it's a bit easier to reason in terms of it, but like it's a bit hard, it's more layers away from the actual thing that you're running.
So at the moment, basically saying that most of it is like working on assembly,
Yeah.
where basically like an approach like C# or Q#
Yeah.
is just going a layer more closer
That's
to
right. Yeah.
what we're used to.
And so there's a team, for instance, at UTS, Ming-Chen Yang runs a team which is working on developing like formal quantum programming languages with, the stated goal of trying to really abstract away all this stuff about, I want to apply a gate between here and here and do this thing and then apply another gate over here, which is kind of the way Circ works.
Okay.
Like he's working development, but this is hard. Like there's a lot of actual fundamental problems in like, how do you do this in a really sensible way? Yeah. But yeah, there's definitely work on that, a lot of work on that now. And I think it's going to be really interesting to see how far that goes because like, you probably shouldn't have to really need to get into the combinatorics of like.
Well, I mean, we
of the
already
thing.
have done it, right?
Yeah.
So, I mean,
Yeah, it'd be nice if people could.
start abstracting from it.
Yeah.
Java for Q.
That's a question. I might have misunderstood at one point. I definitely misunderstood a lot of what you presented tonight. But at one point you said that measuring the state of a qubit has a dependency on the entangled qubit. Something to that effect.
So I said that when you're performing, yeah, that's right. So if you have a given qubit, right, and it's entangled with other qubits, certainly its state depends on the states of the other, well,
Yes.
the joint state of all of them depends on the state of all of those qubits. The individual qubit itself is mixed, right?
So the state will be the same for both qubits. If they're entangled,
Yeah, sure.
regardless which way
Yeah.
they're entangled, whichever the state is, but if they're entangled, once you measure one,
Yeah.
the state will be identical for the other.
Well, it depends on how it was entangled and what the yeah. Yeah.
It's up and down.
Mm,
Okay, so
sure.
independent, you meant that once you know a state, the other state, you know the other state. Not that one state will be
You don't-
independent
well-
of the other state.
Well, okay, that's only if you actually knew they were entangled, yeah. If you didn't know they were entangled or how they were entangled, you wouldn't know that.
Okay.
Because
But
if you look
two
at-
entangled qubits, once you measure one state,
So that's not quite right. So that's only true if you have information passing from one to the other. And you have to like recorrelate the states in order to be able to see that they actually had the same state. So if I was an isolated qubit over here and it's entangled with something over there, if I only could ever look at that qubit, I can't tell if it was entangled or not. There's no way of doing that unless we actually have a communication channel between them. Or if for some reason I knew exactly what the state was.
so the dependency is to verify or to know that they are entangled.
Yeah.
Going back to the verification problem, if some problem is outside of the polynomial time and it's being addressed by some quantum algorithm,
Yep.
but at the same time, the non-verification process poses a challenge itself, like outside as well of the polynomial time complexity. Is there some approach to be taken to verify or to simplify the verification process, or using as well the quantum properties?
Yep, there is, actually. It's a good question. So you're asking, is there a way of doing verification using the quantum properties? I didn't talk about it. It might even be a line over here. But, okay, so it depends on the architecture and how you actually build your process. So there's a way of developing a quantum processor, which we call blind quantum computing, which allows you to basically have perfect encryption from the process. Like, so you have a server and you have a server and a client, okay? So I want to send my computation to the server, and what I can do is I can completely encrypt. There's a way of doing this if I can encrypt if I can send them a quantum state, which can be fed into the quantum processor under the guarantee it's the right kind of thing. Okay, so there's a way of performing that protocol such that both the server can't see what I actually sent them, so they don't know what the computation actually is that they're running, they just run the thing. And I can also verify that they didn't run the thing. So if they didn't run the protocol the way it's supposed to be run, I can actually see that from the outputs that I get back from the server. So that was a really neat discovery. that was found in 2008. I've actually got a line there, yes. But that requires an actual particular physical channel to be there in this process. So you have to actually use a particular type of physical system to do that. This result I briefly mentioned from last year, which was great, basically did that where they took away the quantum channel and did this with classical encryption. So they showed that there's a way of encrypting the messages to the server and forcing the server to do the computation in such a way that both they don't know what it is, but also that I can check that they did what they were supposed to do under the assumption that the learning with errors problem is actually hard for quantum computers, which is pretty neat. It was really, really neat. And the other one has the advantage that there's no assumption. It's just if physics works.
So this is not I'm talking about homomorphic encryption?
It is. It's a homomorphic encryption scheme. It's a really clever, a really neat application of homomorphic encryption.
We didn't talk about that in 77.
Any more questions? Oh, yeah.
Do you have any quantum computing application in terms of AI in the future?
So the question is, are there any quantum computing applications in terms of AI in the future? Good question. So there's an awful lot of proposals right now. So I've totally lost count. The number of proposals, there's a lot. As to whether they're actually will stand the test of time, I don't know. We actually don't know. So the people are really throwing them out there's many every day now. So it's evaluating them is actually a problem. So working out which ones actually will work and which ones don't, which ones make sense, which ones don't, is a significantly important theoretical problem. And how do we assess whether they're good or bad? You can rule some things out, really quickly. There are some tests. So I actually had a slide. It's not quite a machine learning protocol, but on optimization, which I didn't get to. Oh, wrong way. So I mentioned all these sampling problems, and they're really complex things. You can try and imagine that maybe somehow all the complexity in those circuits can be used to solve optimization problems. Turns out not so much. Well, not easily anyway. So there was a really neat paper which it's kind of become known as the barren plateau problem, which is that if you have sufficiently random circuits, and you were the sorts of problems people are trying to solve in AI and optimization right now involve passing your outputs from a quantum circuit to a classical optimizer or subroutine, and then back to another quantum circuit, which you then change and then go backwards and forwards, and you try and do an optimization this way. Okay, there's a bunch of sort of standard algorithms for doing this. There are a bunch of algorithms people proposing for doing this. Now, here's the problem. The problem is normally the classical optimizer, or the thing you're actually trying to optimize is a function of not that many variables. So it's like a Hamiltonian or something like that, like these things which I mentioned. The problem is for sufficiently random circuits for which these sampling arguments work, basically all the optimizer ever sees is noise. The best solution it can see, because they're not powerful enough to actually see the differences in these circuits. So this goes back to the problem of verification. So these circuits are very complex, but they're subtly complex, right? So in order to actually use that complexity, you need something with a lot of power. So you're kind of why using the quantum circuit to the optimization in the first place is run the optimizer. It's probably more powerful than the circuit you're running in the first place, if it was to work at all. So that's a thing. So these are things you have to be careful of and rule out. So that was one thing that people would put forward a whole series of papers about that, and then this paper came all wiped out everything that looked like that overnight. And there's been another few classic examples of there's a whole series of AI solutions which people had proposed using a thing called the HHL algorithm, and they more or less were all knocked out by a 17-year-old grad student at the University of Washington a couple of months ago. So it's called getting Ewinged now. Ewing 10 was the student who did this. She's a great student, and it's become a verb, getting Ewinged. Anyway.
Okay, this will be the last question.
Where do we apply the quantum computing in terms of optimization in a practical situation?
Yeah, so we don't know yet. We're trying to work out exactly where we can use quantum computing for optimization problems. Where it works really, really well, better than a supercomputer on my laptop. That's hard. It's really hard to work that out. And so there's a great example algorithm called the QAOA algorithm, and it's sort of a one-size-fits-all optimization problem. But finding the right set of instances over which this works well is like a really active area of research. Thanks.
Okay, so we can thank our speaker. Thank you very much, Michael.